In our last set of notes, when we were putting together equilibrium expressions and using it to determine K, one of the steps, step 4, said to calculate Q and determine the direction of the shift to the equilibrium. Q is something that is called a reaction quotient, and really the only time it's useful is if you have a reaction and you're trying to figure out what direction it's going, if it's going to the left, if it's going to the right, or if it's only at equilibrium. The way that Q works is very similar to the way that K works. In fact, it's solved almost the exact same way. You set up an equilibrium expression. It looks exactly like the equilibrium expression for K. The only difference is when we solve for K, we put in equilibrium concentrations. When you solve for Q, you're putting in initial concentrations. So let's take a look at how this works and why it works. Okay, let's say we have this equilibrium expression right here. And then let's say our value for K is a certain amount. I'm just going to write down the number 1, all right? And we have a reaction in which the initial concentration of Y is much greater than the initial concentration of X. All right, that means that it's going to naturally want to move this direction from Y to X in order to cause the value for K to reduce down to 1, because if this is big and this is little, it's going to be much greater than 1, so it's going to shift to the left. Now, if X starts out much greater than Y, that makes our K value much, much, much smaller than 1, and our reaction is going to shift this direction over to Y naturally, making Y bigger and X smaller until our K value is equal to 1. And so what we're doing is we're comparing initial concentrations to the ratio of our final concentrations to figure out what direction the reaction is going. In other words, guys, the main thing we need to know is this right here. Okay, if K is equal to Q, then we're already in equilibrium. If Q is greater than K, then our reaction is going to be heading to the left in order to use up products and make reactants. And if Q is less than K, it's going to be going to the right. So those are our major things to know. Equilibrium, if Q is greater, it goes to the left. If Q is less, it's going to the right. So let's take a look at an example problem. So in this problem here, it gives us a value for Kc. It asks us to predict what direction our reaction is going to be going, and then it gives us our initial values. We set this up in a very similar manner to how we did our previous problem. First thing we're going to do is we're going to figure out our balanced chemical equation, which it already gives us, and then we're going to set up an equilibrium expression. Okay, so here's our equilibrium expression, and then all I have to do, because it gives me the initial concentrations of all three of these, all I have to do is plug those initial concentrations into my equilibrium expression, and when I do that, what I'm solving for is I'm solving for Q. Alright, so when we go through and do this, we get a value of Q of 1.33. And so that means that Q is much smaller than K, which was 50.5, it tells us in the problem. And since Q is smaller than K, that means the reaction is going to go from left to the right. So it's going to move towards the right. So let's take a look at another example of this. We have a 1 liter flask filled with 1 mole of H2, 2 moles of I2, gives us a value of Kc. What are the equilibrium constants of H2, I2, and Hi in moles per liter? I'm going to go ahead and rewrite our balanced chemical equation since we always need to start with that. And on this one, I really don't have to bother solving for Q because it tells me I have 1 mole of H2, 2 moles of I2, and I don't have any Hi at all, so it's definitely going to go to the right because I have no Hi. So I'm going to go ahead and set up my equilibrium expression because that's my next step. And then since I really don't have to find Q, I'm going to go ahead and set up my ICE table, initial change equilibrium. Now it gives me the initial amount of I2 and H2. So I've got 1 mole of this, I've got 2 moles of this. Now normally I would have these in concentration values, but since this is just in a 1 liter flask, that means that these mole values are my concentration values, because 2 moles divided by 1 liter is 2 molar. I have 0 of this, and I have no idea what the change is going to be, and I have no idea what the equilibrium concentrations are going to be. So what I'm going to do is I'm going to do this. I'm going to say that this is going to go down by x. This is also going to go down, oops, not plus, also going to go down by x. This is going to go up by 2x because of that little 2 right there. And so this right here is going to be 1 minus x, this right here is going to be 2 minus x, and this right here is going to be just 2x. Now I'm going to take these values and I'm going to plug them into my equilibrium expression. And the reason why I can do this is because I already know what Kc is. It's 50.5. It tells me that in the problem. And so when we do this, we get this wonderful looking little thing right here. Now if I take this and do a little bit of rearranging, I'm going to get this right here and do a little bit more rearranging, and we get this awesome looking thing here. And you know what this means? This means the most wonderful thing in the whole world, the quadratic equation. Yay! So, if you have one of those fantastic calculators that will solve a quadratic equation for you, please, please, please use it. If not, you get to use the quadratic equation to do this. Hooray for you. Remember, when you go through and solve a quadratic equation, you're going to get 2 answers. So to figure out which one of these is the right answer, whether it's this one here or this one here, we're going to head back up to our original ICE table. Notice that our equilibrium concentrations of H2 and I2 are going to be 1 minus x and 2 minus x. So x cannot be equal to 2.323 because that would give us negative concentrations, which is impossible. And so that means that this right here has to be our value for x. Now that isn't our final answer, it's just our value for x. To get our final answer, which is what are the equilibrium concentrations, I have to plug that x into this right over here. So if I do that, I get these numbers right here as my equilibrium values for my 3 substances. If I went ahead and plugged them back in to my equilibrium expression right here, I should get 50.5. And if I do, that means that I probably did it right.